Okay, hi, I'm Richard from Telesoft, and one of the questions I get asked most often is what is an FPGA? So let's discuss. So an FPGA stands for Field Programmable Gate Array. So that is an array of programmable logic gates that you can program in the field. So let's take a look at what's inside them, because that might help. So this is a view of a chip planner of an Intel FPGA. The things we're discussing today are representative of most modern FPGAs. So first, if we start in the corners of this chip, you can see these transceiver banks. So transceivers are transmitters and receivers. In modern FPGAs, you're looking at tens of gigabits per second per transceiver. Right behind the transceivers, you've got the hard IP. I can tell you, just from knowing that they're right next to the transceivers, these are going to be PCIe or Ethernet Max, so very high-speed serial interface protocols. Other examples of hard IP you get commonly are external memory interfaces, so DDR3, DDR4 controllers, or even quad-core ARM processors are pretty commonplace in modern FPGAs. Other things that you get inside FPGAs are registers. These are really common, you get millions of them. All they do is latch their output, or latch from their input to their output on a clock edge. We'll discuss more about why these are important a bit later on. Others that you get in FPGAs are I/O lane circuitry, so this controls all the physical pins on the device. It allows you to control single-ended or differential signaling, different voltage levels, if you've got open drain, inputs, outputs, etc. This controls all of that. We've also got RAM. This is regular memory, random access memory. It comes in blocks. You can join the blocks side by side to hold wide data elements, or you can stack them deep to hold lots of data elements, or you can stack them wide and deep to hold lots of large data elements. They're very flexible, very programmable, and they can cover most things that you'd like to do inside a chip. Next, DSPs. So if I zoom in a little bit on this slide, you get these banks that are colored down. So some of these are block RAMs, some of these are DSPs. DSP stands for Digital Signal Processing. So these are little blocks of logic that are very good at doing maths very quickly. So that can be addition, subtraction, multiplication, multiply, accumulate. And the DSP slices are just used for that. They're very fast at a very specific task. The final thing we have are LUTs, or a lookup table. So we'll find out about what they are on this slide. So if you haven't done digital logic design before, this is a simple AND gate. It's called an AND gate because its output goes high when both its input, or inputs A and B, are high. And on the left here, you can see this is a truth table. So this shows that when both inputs are high, the output goes high. So this truth table can be programmed into a programmable lookup table. And this is the basis that lookups, or lookup tables, start implementing programmable logic. So if we go to a slightly more complicated example, there's a few more logic gates here, but if you want to follow through on the slide, please feel free to work it out. But the truth table there should correspond to the logic that's shown. So this has 4 inputs. Most FPGAs that we use at Telesoft have 6 input lookup tables in them. FPGAs come anything from 4 input LUTs to 8 input LUTs, but 6 is kind of a pretty standard middle of the road that most chips have. They're all programmable, and on the Stratix 10 FPGA, for example, there are 1 million LUTs. So this gives you a little idea of the scale of how many lookup tables you have in a sort of modern high-end device. You can get more, you can get less. It's very device dependent. Next, we're going to talk about how the compiler works. So FPGA compilation, particularly if you're from a software background, FPGA take quite a long time to build. So we're going to talk about why the process takes the time that it does. So the first thing the compiler does is very much the same as any other software compiler. It'll do a syntax check and elaboration. So it's checking the code you've written is syntactically correct, and that all the functions that you called are declared somewhere and are also correct. The next thing it does is what's called synthesis. So this is taking the syntax checked code and it's turning it into the elements inside the FPGA that we've discussed. So this is a netlist view, and it's taken all the code and it's turned this into logic gates, into registers, into DSP slices, into block RAMs, and this is what you can see on the slide behind me. This looks messy, that's because it is. It's very, very complicated. This is quite a large design, and the image you're seeing here is a very small section of a large design. So this does take a little bit of time for the tool to work this out. The next stage is the tool will take your synthesized netlist, and it has to fit this to the device. Fitting comes in 2 stages. There's place and there's route. Granny with a shotgun here is representing the place stage. So the first thing the compiler will do is it has to just get an initialization or a starting point for all of your logic on the target device. And it does this with a semi-intelligent shotgun blast. So it takes all of your logic and just chucks it on the device. Then it iterates through this. So the initial placement is just an initialization. It's then moving all your logic around, all your DSP slices, all your block RAMs, and it's trying to find a global optimum placement for all of your logic. The second stage of fitting is routing. So the routing is when it then has to connect all of the placed elements and it has to route them to all the elements they're connected to. Again, routing is an iterative process, so this goes through many, many steps trying to find the optimum routing for your entire design. It's no good just having one path that's really fast if it sacrifices all the paths around it. So the router does take a fair amount of time. Even on very high-end processors now, you're looking at several hours or maybe even tens of hours for a really large design on a modern FPGA. The final stage of the build process is a lot quicker, so there's the assembler and timing analysis. Assembler is the process of taking your placed and routed design and turning it into a programmable bit stream for your target device. And then timing analysis is how it checks that your device will pass timing. Now timing closure or passing timing, timing clean, these are phrases you will start to hear as you work with FPGAs. So we're going to talk about what that actually means. So timing closure is the tool measuring the paths from every register to every other register or from I/O pins on your device. Now there's a lot of paths for it to measure, but it actually does this quite fast. And it has to measure the total delay. Now the delay is made up of two things. You get logic delay and routing delay. So logic delay is the amount of time it takes for your signals to get through the lookup tables or through RAMs. And the routing delay is the amount of time it takes those signals to pass through the routing that the compiler has chosen to use. Now, you're aiming for your logic delay and your routing delay to be less than your clock period. So if we take the example of an FPGA running at 333 megahertz, you have a clock period of 3 nanoseconds. So you need to get from one register to the next register in less than 3 nanoseconds. Sounds quite fast, but this is very achievable in FPGAs. So the next thing is all of this sounds quite complicated. So why do people bother using FPGAs? What benefits do they bring to us? Well, the first thing, it offers massively parallel processing. So let's think about what this actually means. If you think of an FPGA running at 300 megahertz, but then you compare it to a processor running at 3 gigahertz, you'll often think, well, how is an FPGA any faster than a processor? The processor is 10 times faster. Now the difference is due to the parallel processing. So a CPU or a processor core will operate one instruction at a time. So at 3 gigahertz, it's operating at 3 billion instructions per second. So an FPGA only runs at 300 megahertz. This sounds 10 times worse. But the FPGA does everything on every clock cycle. So if you implement an FPGA with 1,000 functions, and each of those functions would take a processor 10 clock cycles to implement, you're looking at 10,000 clock cycles for your standard processor to implement the same thing. But an FPGA can do this every single clock cycle. So suddenly running 10 times slower is insignificant because overall you've got a 1,000-fold improvement in your performance. So this massively parallel processing gives huge acceleration. It doesn't matter if you're accelerating maths functions, if you're doing fingerprint hashes, anything like that. Anything that a processor can do, an FPGA can also do really quite quickly, particularly if it's an iterative process. Things like hashing algorithms or compression, decompression, encryption, decryption, these things are really well optimized for hardware implementations. Now, counterintuitively, this huge acceleration also gives you a massive power efficiency. So if you consider if an FPGA is 1,000 times faster than a processor, if you are running 1,000 processor cores, you're going to use a lot more power than one FPGA. So all of this massively parallel processing gives us acceleration, which also gives us huge power savings. Pretty cool. So just in summary, what is an FPGA? Well, it's transceivers, DSP slices, LUTs, I/O registers, hard IP. What does the compiler do? What does it work? Well, it does syntax checks, elaboration, it does the filler, which is the place and route, and then assembler and timing analysis. And what does timing closure mean? Well, it's the time measured from one register to another register, including the routing delay and the logic delay, and you want that total delay to be less than your clock period. And finally, why do people use FPGAs? What benefits do they bring to Telesoft? Well, it's this massively parallel processing that gives us huge acceleration and in return also quite a cool power saving. So that's everything for today. I hope you've enjoyed it and we'll see you soon.